Okay, everybody, this is another one of our um, recorded lectures. And so we're starting on chapter 5 of um, the text, which is about bipolar amplifiers. So, in chapter 4 and in our previous lectures, we talked about the bipolar transistor itself and how it could be used as an amplifier. So, for example, we had a bipolar amplifier circuit like this with an NPN transistor that we looked at quite a bit, with this, the base being the input and the collector being the output. And we showed how this had a few different models. One of them was the large signal model, where you have a diode in the base, you have a current source, and you have the resistance of the collector. So this would be the emitter, base, and collector. This is a current source where I sub C is I sub S exponential of the base emitter voltage over VT. And then, so this is a large signal model. The small signal model here is, we had R sub pi, and we had a current source. That's the GM V sub pi. And, we'd have the R sub C and the emitter here, base. So we basically looked at this as an amplifier circuit. I hope everybody saw how this was basically, if you followed some design parameters, you could amplify, meaning you have a small signal here on the input, and you could get it would be inverting, so a small signal on the input, and you'd get a bigger version of that signal on the output. So that was the introduction to amplifiers and the transistors. Now, there's a bunch of things, second order effects, that come into that when you're building this amplifier. And those are what we're really so we're gonna talk in more detail about this amplifier. So we're gonna talk about, this amplifier is gonna be, let me redraw it here, is gonna be interacting with other circuit elements. So say this is our amplifier. So we said this is the input and this is the output, but we didn't talk about what would happen with a typical input. So a typical input has some kind of, it's not a voltage source completely, but it has some kind of a resistance. So let's say, if, we use the case of a microphone. A microphone has some resistance built into it. So the question is, what's the effect of having, and it's very typical. Almost anything that drives an amplifier has its own source resistance or source impedance. And then same with here, like let's say if you were gonna drive a speaker has its own load resistance. So what does that mean? How does this being a source resistance and this being a load resistance, how does that affect the design of our amplifier? Okay. The other thing we did was we said, okay, well, we need to bias this amplifier at a certain bias point. And we did something kind of cheesy, like we said, okay, I'm just gonna draw a battery here in series with my input, and I'm gonna make this battery be 800 millivolts or something like that to basically create the right bias here. And by the bias, we meant this transistor. If I look at the base emitter voltage versus the collector current, we want this amplifier to be working at a place where I have a reasonable amount of collector current, so that I get a certain amount of gain, certain amount of performance. We looked at all those in detail. But in a real world, you don't have, I mean, you have batteries, but it's not practical to put a battery at the input in series. So basically you have to design some kind of a network on the input to provide a bias to the circuit. And that ends up actually being a pretty detailed and difficult task. I think a big part of amplifier design is actually always, whether you're talking about bipolar transistors or MOS transistors, biasing is a big part of it. So those are the general concepts we're gonna cover in the next couple of lectures, okay? And so we're gonna talk about the input-output impedance. We're gonna talk about like some different biasing circuits. I'm probably not gonna talk much about biasing of PNP. I'm just gonna really focus on biasing NPNs. And then afterwards, we're gonna just talk about some other amplifier topologies. This amplifier topology is called the common emitter stage. But given that we have 3 inputs, it's always possible to connect this transistor in other ways, in a bunch of different ways. In fact, I guess you have, one way to look at it is you have 8 different ways, or is it more? I don't know, of connecting this thing. And a few of those are useful in their own ways. So we're going to talk about some different amplifier topologies than just a common emitter. Okay, so let's talk about input and output impedance of an amplifier. So in a real world, again, if you have something driving your amplifier, it has some kind of a source resistance. This is absolutely typical. Like always, you have the situation. Sometimes the source that you have might have a very low resistance, source resistance, you know, maybe it has 1 ohm source resistance or a fraction of an ohm. That's usually a very good thing. But a lot of times, you know, this might be another amplifier like yourself, or some circuit like a microphone. In this example, we can model a microphone as a perfect voltage source with a 200 ohm resistance in series. And then whatever your amplifier drives also could have a load resistance, and that's pretty typical again. And in this case, we have a speaker with a very low load resistance. So typically what you like, and I'm sort of generalizing here, typically what you'd like is, in an ideal world, you would like your sources, whatever's driving the amplifier, you would like it, or life would be a lot easier when you're designing an amplifier if your source has a low resistance, because as you'll see, then you can it's easier to ignore or easier to design the amplifier for its input resistance. And then conversely, if you're driving any kind of load, typically like 99.9% of the time, or maybe all the time, I don't know, you would like it to have a very high resistance, because that is easier for the amplifier to drive that resistance. Well, most of the time, you'd like to have a low resistance or high resistance, I'm sorry. So this 8 ohm is really bad news for an amplifier. It's very difficult to drive a load resistance like 8 ohms, and we'll see why. Okay, so if we sort of dig into the amplifier, so this is drawing sort of the input stage of the amplifier, okay, or let me just draw it this way, is just for the sake of discussion, let's say this amplifier was our simple common emitter amplifier. So what we're drawing here is basically V sub m plus minus 200 ohm R sub m. I'm drawing basically this guy here. And this Rn is the input resistance of this bipolar transistor. And like as a spoiler, I guess, if you remember in the small signal model that there's this input resistor R sub pi at the input of our amplifier. So we just really sort of care about this essentially. And that's what it looks like here. So this Rn, as we'll show in this configuration, this Rn would just be R sub pi. Okay, so, and you remember that R sub pi is something we have a control over. So R sub pi is beta over G sub m. So by the beta is a function of our transistor, but G sub m, as again you remember, is a function of the collector current. And as designers, we have control over, we can design that collector current to be what we'd like, you know, within constraints. So we can adjust this R sub pi somewhat, this input resistance. And notice what's happening. If you have this input resistance, what this is basically a voltage divider. So, you know, your microphone has, in this example, has a 10 millivolt swing. But what your amplifier really sees is not the full 10 millivolts swing, but your amplifier, this is where it senses the voltage, right? And that looks like a resistive divider, 200 ohms plus R sub in times V sub m. So that's really this is the real input of the amplifier. I don't know what you want to call it. Let's say call it sense. Now imagine if this Rn is a low number. Like imagine if this Rn, as we'll see, like let's say if it's 100 ohm. Let's see 100 ohms. Let's say 200 ohms. Let's say it's 200 ohms. That's a good example. If this is the same as this, then this resistive driver basically cuts my input voltage by half. So instead of seeing a 10 millivolt swing here, if this was 200 ohms, I would see a 5 millivolt swing. So even before you get started, you've lost half your gain. So you got to basically end up building this amplifier with twice as much gain as you'd hoped for, just because your input resistance is too low. And this is something you have to like account for, okay, or somehow deal with. Same type of situation on the output. Okay, so if you are, again, if we're driving the same common emitter amplifier, and I'm looking at the output, so like here, okay, so imagine I'm using a common emitter amplifier. It's driving this 8 ohm resistor. It's driving the speaker load, so that's the speaker load. And if you remember, as we'll see, if you're driving something like this, you'll have the small signal output is got the sort of the early effect resistance, and it's got your R sub C. So again, you're doing a resistive divider, or actually it's more like not the parallel combination of resistors, sorry, where instead of having this as your output resistance for your gain, you actually have to add this in parallel. And you can see, like, you know, the resistances, I don't know if you guys remember from chapter 4, these were, you know, typical numbers that we were looking at was like a kilo ohm or whatever to get your gain. And remember, the gain was GM R sub C. So if this was a kilo ohm, we'd get a certain resistance. But now imagine sticking an 8 ohm resistor in parallel with a 1 kilo ohm. That parallel combination is going to be very close to 8 ohms. And now you've dropped your gain by a factor of like 100. So your output resistance has gone, by sticking this guy in your output resistance has gone from a kilo ohm to around 8 ohm. And so your gain has gone down by more than a factor of 100. So again, you have to, you can see this is a pretty tough case of driving a speaker. Again, that's a difficult load to drive, but it's an important part of our consideration when you're designing the amplifier. Okay, so the first thing is let's show how we calculate the input and output resistances of our amplifier, because we have this load and then we got to figure out what our input impedance of our amplifier looks like. And I gave you guys again some spoilers about what it would look like in this case of a common emitter amp, but we're going to have there's lots of other circuit types, amplifier types, other circuit types. So we need to talk about a general way of calculating input and output resistance. So the general way of doing that is by, let me just make sure I've got my notes all worked out. Let's do, actually, before we do that, let me just run a couple of examples. So a couple of specific examples of what the situation looks like. Okay, so let's say we have, I think this is one of the examples in the book. It says, okay, like what happens if on input resistance, of our circuit here, okay? It says like sort of figure out what happens if this Rn is either 2K ohm or 500 ohm in each case. Okay, so input resistance for Rn, or the input resistance of the amplifier, being either 2K ohm or 500 ohm. So in other words, what our circuit would look like would be, this is the microphone, and it has a 200 ohm resistance. And then imagine if this is our amplifier, and this guy is 2K ohm, for example. Okay, so what is basically so this is where our input, the real input to the amplifier is, okay? Or some people call it V-sense. That's where you're sensing your input voltage and amplifying it out. So it's a, resistive divider, ends up being a resistive divider here, as you can see, because you got this 2K ohm and you got this 200 ohm. And in this case, your V-sense, or your real input to your amplifier, is 2K ohm over 200 ohm plus 2K ohm times the microphone output, and it ends up being 0.91 V sub m. So not a great situation, but it's not the end of the world. You've lost 9%. You've lost 9% of your signal amplitude from the get-go. Before you've even done anything, you've lost, like, you got to make up this 9%. You're not at 100% of the input, but it's still not the end of the world. Okay, not so bad. So 2K ohm, when you're comparing a 2K ohm input resistance to a 200 ohm source impede resistance, okay, you can live with that to some extent. Okay, you can make up for that. Now let's look at the case where the same thing, but you have a 500 ohm input resistance. Now this is going to be a lot worse of a situation, because in this case is, we've got 500 ohms over 200 ohm plus 500 ohm V sub m, and this is equal to 0.71 V sub m. Okay, in this case, we've lost from the get-go, we've lost, what is this, 29% of our signal going into the amplifier. And again, that's power consumption. Like, you got to make up for that gain. And when you make up for that gain, you got to increase your power consumption. Like, you got to pay for that somehow. So it's not a good thing. And you can see generally, it's much better generally to have a high input impedance, high input resistance in your amplifier than you have, like a 2K ohm is better than a 500 ohm. And if you had this was 10K ohm, it'd be even better. But at some point, there's trade-offs, because as in this amplifier, as you'll see, to get the higher resistance, you need to lower the collector current, which means that you'll have less of a gain. So a lot of circuit design are these trade-offs. But again, this is an example, and it shows you what kind of an effect, how important this input resistance could be to what you're actually inputting to your amplifier, and how a higher input resistance is better from this sense to be for you to be driven. Okay. Let's see. Okay, so now let's look at a case where we're looking at the output resistance. So how about two cases? If output resistance of amplifier is 10 ohms or 2 ohms. Okay, so now we're looking at the output of the amplifier. So it's as if we have the amp output voltage that you would normally expect after you design it, but there's really a output resistance there. And in the first case, this is 10 ohms, and it's driving our speaker, which has an 8 ohm load resistance. So let's see what that does to our output signal. Okay, so in this case, the output signal is also a resistive divider. It ends up being 8 ohm over 10 ohm plus 8 ohm times the amp voltage. And this ends up being 0.44 amp. So this is even worse than the input resistance. So having, in this kind of a situation, we've cut our amplifier output voltage out by more than half. That means that we have to design our amplifier to have twice as much gain as we were expecting it to, just to be able to deal with the input resistance of the load. Okay, and then so the second example is we have the amplifier voltage and we have a 2 ohm output resistance driving the same speaker load. And in this case is 2 ohm over 10, 2 ohm over, what am I saying? I got it wrong. We got 8 ohm over, this should be 8 ohm, 8 ohm, 2 ohm plus 8 ohm. Okay, in this case is V amp. So it's equal to 0.8 V amp. So in this case, I've lost 20% of my signal, which isn't great, but it's certainly better than this case, than losing a factor of 2. So this is an example showing what's preferred in terms of input and output impedance or resistance. So you can see it's better to have a low output, generally it's better to have a low output resistance and a high input resistance for an amplifier as a general case. That way you lose less of your signal. So high input resistance is good, low output resistance is good. You'll lose less of your signal that way. By the way, as a side or a general note, is you'll hear a lot, and you'll hear me also say it. I talk about input impedance and output impedance. So a lot of amplifiers, this is just for your interest. I don't want to confuse you. It's sort of too early now on, but I just want to let you know about why impedance versus resistance. So generally, circuits aren't just resistive. There's capacitors, input, capacitive inputs. There's even could be inductive type of inputs or outputs. So generally, in a general sense, people talk about input and output impedance. And you generally talk about, same with source and load resistances. Generally, this would be could be capacitive components here, inductive components, same here. So people also talk about source and load impedance. But in this class, impedance and resistance are the same because we're ignoring capacitive and inductive parts of the circuit because we're having an early introduction to these things, or a more simplified introduction. So anyway, if you hear me say input impedance, output impedance, or source impedance, load impedance, just interpret that as being just resistance in whatever case, but with the impedance being more general type of comment. Okay, so that was some of the examples. Now let's look at how you would, if you have any kind of circuit. So this shows you a general black box of a circuit with 2 inputs, 2 outputs. Okay, like how would you figure out the input resistance? Well, first of all the input and output resistance calculations or impedance calculations are done in small signal domain. So all input, output impedance calcs are in small signal domain. So that's one. Okay, so the first thing you do is you would go, okay, I'm gonna put my circuit in the small signal domain, so represent it there. And then I'm gonna put in a test voltage on the input. So like I said, real sources have resistance associated with it, but this is a test input. So if you're really going to do this in the lab, you would try to find a voltage source. You wouldn't use your microphone, you'd use like a voltage source with a very, very low output impedance or output resistance. Or when you're analyzing it, you would sort of assume something that does not have an output resistance. So you'd put that on the input. You would leave the output sort of floating. You wouldn't drive anything on the output. And then you would put a wiggle, you'd give some kind of an input here on V sub X, and you'd measure the current going into your device, whatever that device is. This could be a really complex device, or it could be our simple single transistor amplifier. Whatever it is, it's the same. So this is just like a black box. And you would put try to get as perfect a voltage source as you can find, modulate the input, and measure the current going in. And the input resistance, so Rn, would be V sub X over I sub X. Okay, so again, in the lab, you would just measure the current for your input voltage. You'd get that ratio, and that becomes your input resistance. Or when you analyze it, you have to plug this into your circuit. Okay, for the output port, what you do is, again, you put as perfect a voltage source on your output as you can, except this is just for the output port. For that, you would short the input port. So notice here, we did not short the output. We didn't short the output. We left it open in our analysis. But in the case of the output port, you have to remember to short the input together. And then you put your voltage source here, measure the current. And again, the R out ends up being V sub X over I sub X. So if you were going to do this in the lab, you would short the inputs to your amplifier or whatever circuit you got. You would find as perfect a voltage source as you could find, modulate it or wiggle it around or whatever, and you measure this current, and that ratio gives you the output resistance. Okay. All right, so let's sort of have an example here. I'm going to work it out. Let's do what current template? Nope, wrong one. Sorry, guys. Got the wrong template added. Let's say squared paper is what I want. Okay. So let's say we want to do the input impedance of common emitter amp. So here's our common emitter amp. By the way, in notation, I think I've thrown this around already, but this is just to make life simpler for drawing. So when you see this, and you see this, it's the same as this. Okay, so it's just this is like a very common thing to basically you draw this, which says, you know, this node is going to a voltage source or a battery of this value, VCC. So that's what this means. Okay, so R sub C, we have, let's call this guy Q1. This is the output, and this is the input. Okay, so I'm trying to figure out the input resistance. And remember, what we're trying to do in a general way is we're gonna go take 2 steps. Okay, so step 1 is use small signal model. Okay, and what does it look like here? So we've got a R sub pi, and we have our GM V sub pi, and we have our early resistor, our own transistors resistor, and then we have our collector resistor. Okay, and sort of V out is here, and emitter is grounded. Okay, so this is our small signal model. Then step 2 is I'm going to take this guy and I'm going to stick in a perfect voltage source, V sub X, on the input. And I'm going to basically try to figure out what, if this is I sub X, V sub X, what is my I sub X? And that ratio, so our input resistance is going to be V sub X over I sub X. Okay, so what would this look like? Okay, so, well, when we look at this circuit, this input is all your voltage source sees. Okay, notice this point is grounded. Okay, so basically this input sees this R sub pi resistance. So basically our input resistance is V sub X over I sub X is equal to R sub pi. Okay, so that's our input resistance in this stage. It's pretty simple. It's just R sub pi. Okay, so, and remember, so now let's say, so that now we know our input resistance of a common emitter stage is just the R sub pi of the transistor. Now, R sub pi is something we have some control over as designers. So the equation for R sub pi is beta over G sub M. So beta is given to us, or I guess you have some choice there. You can buy a transistor with higher beta, Okay, but let me just write this up more. And G sub M is I sub C over V sub T. So we've got beta V sub T over I sub C. Okay. Now, so that's the equation for the input resistance, like what control we have over it. Okay. So remember, we want higher input resistance. Generally, higher input resistance is better. So this shows that to do that, we have, so V sub T is a constant, you can't do anything about it. So you got two choices if you want to increase this. So either you buy a transistor with high beta, or you lower your I sub C. So those are your two options. The transistor with higher beta, I guess, you know, that's generally a good thing. So you'd like a high beta. But if you lower your I sub C, so it's good for your input resistance, but here's an example of a trade-off is if you lower your I sub C, as we'll see, and this is sort of like the interesting part of your circuit design, lower I sub C trades off input resistance with gain. Because remember, gain was, in the small signal domain, was GM RC, or R out, let's call it. And GM was IC over VT R out. So you lower your input resistance when you lower I sub C, but you're also reducing your gain as you're reducing I sub C. And so for each case, you're going to have to do a trade-off in your design to figure out which one gives you the bigger bang for your buck, because, and it usually ends up being, you know, what's the source resistance and what's your load resistance, about what these trade-offs would be. But because you could just keep reducing your I sub C to increase your input resistance, but let's say your source had a pretty low source resistance, after a while, you know, you don't gain very much once your input resistance goes higher than a certain number. And the fact that you're reducing your gain hurts you more. So it's a trade-off, and we'll see some examples of that. Like everything in engineering, you got, you know, the big part of the game is trade-offs. Okay. So let's see. So now let's look at the output resistance. Okay, and again, you have a case where when you want to do output resistance, you're going to have to, it's again a two-step procedure. It's actually a three-step procedure. No, two-step procedure, sorry. Two-step procedure is, step one is, it's a question of whether we wrap step two into two steps or one step. So just one, probably one step's enough. So step one, create small signal. So I'm talking about this now. Create small signal model. Step two is, this is sort of two steps. So A is short your input, and B is put perfect voltage source and output and measure current. So again, what you do is you short the input, you put a voltage source here, and you measure the current. And that ratio the R out ends up being the ratio between those two things. Okay, so the difference between the input resistance and the output resistance is that the input resistance, you just leave the output the way it is. The extra step in the output resistance is you have to short the inputs together. Okay, so let's look at that. Let's look at an example of what that looks like. All right, so let's look at the case for the simplest case we can think of. Our example is the output resistance seen at collector of NPN or bipolar. So basically, we have our transistor PN, and here's our collector, and we want to see what's this R out. Okay, so step one is small signal model. And that looks like R sub pi, V sub pi, and G sub M, V sub pi. We have our early voltage resistor, R sub 0. Okay, emitter is grounded. So that's our small signal model. And step two, let's copy this guy over. Okay, so here, step two, first thing we do is we short the input. So whoops. I short the input to ground, and then I put my perfect voltage source here and try to figure out what I sub X looks like. Okay, so that's a two-step procedure. And then R sub out is just V of X over I sub X. Okay, so let's take a look at what this circuit looks like. Now, when you want to look at the current on the output, it's made out of two components. So there's a current that goes through this resistor. Okay, you have a voltage V sub X across this resistor because the other end of the resistor is ground. And so there's a current I sub X goes through here. And then there's another current going to this current source, G sub M, V sub pi. So we got to figure out what V sub pi is to figure out this current. So let's look at V sub pi is defined here. Let's look at it. Well, so one end of this resistor, this input resistance, is hooked up to ground because we shorted it. And the other end is also hooked up to ground because the emitter is at ground here. So V sub pi is just equal to 0 because both sides of this resistor are connected to the same voltage. They're both connected to ground. So V sub pi is 0, and that means that G sub M, V sub pi is also 0. Okay, so basically means that because this voltage is 0, this guy basically goes out of the picture, and the only current, I sub X, the only current is over into R0. So my R out ends up being, so it's again defined as V sub X over I sub X is just equal to R0, which is just the early voltage. So this is R0 is just early effect, I guess, or early effect resistor. Okay, so that's an example of output resistance. Okay. Okay, so those are these two examples. Now let's look at one more example. And that's because we said this was sort of like a general procedure, right? So let's look at the resistance seen as the impedance seen as at an emitter. Impedance seen at emitter. So in this case, we're actually looking at, we no longer, in this case, we're grounding the emitter. Notice I talked about, whoops, we've been very focused on this amplifier sort of circuits or topology or whatever you want to call it, where we had the emitter grounded. But it doesn't always have to be this way, right? We have 3 inputs. So we can do what we like with those inputs. Some of those things are going to give us useful circuits and some won't. But you could have circuits, specifically the emitter follower, where the emitter is not grounded, but it's really your output. So we'll come to those later, but for now, let's see if we did something like that, what would the output resistance look like? Okay, so back to this. So in this case, again, something we haven't really looked at so far, but let's say the emitter is driving the output. Like, don't get too wrapped around what that would mean or what I would look like for the second. Just think about its resistance, what that you'd see. Okay, so we have the tools we need to analyze that. Step 1 is we create a small signal model. Okay, that's again R sub pi, V sub pi plus minus. You have the emitter here. You have G sub M, V sub pi here. We have R0. Okay, and remember in the small signal domain, whenever we have a voltage source, when you're going from large signal to small signal, voltage source is equal to a short. Okay, so because this is, let me erase this, sorry guys. Let's see. This is equal to this is grounded, and in small signal, it looks like you're shorting through it. So it looks like you just have a short to ground. So I would put a short to ground here, where this is. Okay, so this is a pretty important concept. Whenever you see this, it's really a voltage source or a battery, and you just have to short through that voltage source or battery in small signal, and you get a short. So don't forget to do that. Okay, important thing. Okay, so that's our small signal model. And then step 2, we take that guy. And the first thing we do is we short the input. So the input in this case is the base. The input is the base, so I got to short that input. And then I'm going to put a perfect voltage source on my output, which in this case is the emitter. And I'm going to measure the current. So again, this is like a very general approach of figuring out this 2-step procedure for figuring out output impedances. no matter what you got a black box, okay, you short the input and you put your voltage source at the output and measure the current, okay? And so here we are. Okay, so now for the sake of discussion, for the sake of making our life a little easier, because it makes the analysis more complex, let's say that V sub A, so the early voltage is infinity, so that R0, so we can basically neglect R0. So remember R0 is I sub C over V sub A. So this would mean that if V sub A is infinity, we can just sort of get rid of this guy. Okay. So now we're looking at I sub X. And I sub X is made up of two components. It's made up of a current coming through here and a current coming through here. Okay. So I sub X is flowing into this node. And this guy is flowing in here. So basically what we have is, so if we had I sub X was flowing this way, if that's how we were measuring it, then it would equal to these two. But because you've defined I sub X as flowing into it, what we have to do into the node, you'd say that minus I sub X is equal to I flowing through R sub pi. So I'm going to call this I flowing through R sub pi plus G sub M V sub pi, which is this current flowing in. So we got this guy plus this guy is the negative of this guy. It's going in another direction. Okay, so let's see, where was I? Yep, so let's say we have, let's see what we got here. So interestingly enough, so we've got V sub X placed here, okay? And so just looking at V sub pi here, right? So V sub X is on this side of the resistor and ground is on the other side of the resistor. So V sub X, V sub pi is actually minus V sub X because of the way I've defined V sub pi. V sub pi, I put the positive and negative like this across this resistor, but V sub X's positive thing is where the negative of V sub pi is. And the ground or the negative side of V sub X is where the positive side of V sub pi is. So V sub pi is minus V sub X. And therefore, I R sub pi would be V sub pi over V sub pi over R sub pi or minus V sub X over R sub pi. Okay, so that's this first current. This guy is minus V sub X over R sub pi plus G sub M. I'm going to plug in V sub pi here, and again, that's minus V sub X. Okay, so it's minus V sub X. Oops, clean this up a little bit. So we take the minus V sub X out, and we end up with 1 over R sub pi plus G sub M is equal to minus I sub X. So these guys cancel each other out, and R out is V sub X over I sub X is equal to 1 over R sub pi plus G sub M. Okay, so that's the output resistance looking into an emitter. Okay, so let's look at this a little bit more about what this actually is to get a feeling for what this might look like typically. Remember that R sub pi is beta over G sub m. Okay, beta is typically on, you know, the level of about 100 or so. So that means that if you're looking at this guy, typically, because beta is high, so this is equal to 1 over beta over G sub m plus G sub m. This is usually ends up being like, you can kind of ignore this because beta is a large number over G sub m, and you'd end up being with approximately 1 over G sub m is your output impedance. So the nice thing, it ends up with a emitter follower, or sorry, with a looking at the emitter output resistance, is that you typically, this 1 over G sub m, so, you know, the G sub m's that we were looking at were like what? I think our G sub m's were, I don't know, like 1 over 25 ohms, that kind of thing. So all of a sudden we have, you know, if you have R out is 1 over G sub m, is R out is equal to 25 ohm, which is a pretty low resistance. And you can also control G sub m. We could always pump more current through this. So G sub m is I sub C over V sub T. So we can pump more current through this guy and reduce our output resistance. And remember that as far as output resistance is concerned, a lower number is better. So what you typically see a lot in amplifier stages is you end up seeing so again, this is kind of a aside for you guys to get a feel for these things, is you'll see something like a common emitter stage, and this gives you high input resistance for your load and sort of, you know, gain, and you tend to follow that up with something like a stage like this guy. It's a little bit more complicated, and that's driving your output. And what this guy gets you is a low output impedance or low output impedance. So you can drive your outputs easier. So a lot of, you know, we're even in this chapter, we're mostly going to be talking about single transistor stages. But when you look at a real usable amplifier, almost always it's made out of multiple stages and many transistors, usually, you know, somewhere between, I don't know, typical amplifiers are somewhere between 5 and say 30 transistors or something. And they're all sort of put in there. There's these different stages are put in there to deal with various things. Like if you want you want to get a combination of high input resistance, low output resistance, you want high gain, various other things, linearity, you know, there's a lot of stuff to consider, but they're made up of these stages that, you know, single transistor stages or things like that. And they give you different characteristics. So that was the emitter impedance of a emitter output. And so, so that's where we're sort of stopping with impedances, okay? And the concept is the procedure is very simple. Again, going back to our procedure, what you do is if you're looking at an input port resistance or input resistance, you create a small signal model, you leave the output open, You put a perfect voltage source on the input, measure the current going in. That's your input resistance. For the output ports, you do the same, except you have to short the input. So it's the same procedure no matter what. I don't have a specific circuit here because it's generic. It's like whatever circuit you got, whatever network you have, you can do this too. Okay. Now the specifics of doing it, yeah, it's you saw like there's sort of like tricky aspects here, but if you follow the step-by-step procedure, the concept is fairly simple. Okay. And there's certain general things we learn from that, okay, having to do with the bipolar transistor that are good things to remember. So rule number one was that if you look at the base, the impedance is just R sub pi, okay, as long as the emitter is grounded. As long as the emitter is hooked up to AC ground, the input resistance is R sub pi. That's very important. Don't forget, guys, that it's not always the case where this is, you could easily have a circuit where your emitter is connected to your resistor. And as you'll see in this case, the input resistance gets more complicated. So this thing, if emitter is AC grounded, is important here. If that's the case, the input resistance is R sub pi, okay? And furthermore, R sub pi is beta over G sub M is equal to V sub T beta over I sub C. So the lower the I sub C here, the higher this input resistance is. Okay, so that's rule one. Again, so rule two is and this is the reason for these rules, or these are pretty usual stages. You see these kind of things a lot. You'll see an emitter grounded with the input through the base a lot. You'll see an input grounded with the output through the collector a lot. And in that case, in the case when the emitter is grounded, okay, and the input is through the base, the resistance looking into the collector is just R0, which is the early effect resistance, which is V sub A over I sub C. Okay, and then looking into the emitter, okay, and so R out, looking through the emitter, is 1 over G sub M. And of course, this is if the base is being driven as, or AC grounded is the way to look at it, okay? And ignoring the early effect. So if these two are set, base is empty, we get this 1 over G sub M at the output of the emitter. And these are like really important stages. So you see this a lot for input stages, and you see these two depending on your output as output stages. So these are really important rules of thumb to remember. Okay, guys, so I'm gonna stop here. This is the input and output impedances, okay? And so again, a relatively simple concept and a simple set of procedures. And some rules of thumb to remember, useful to remember that, hey, if I want a high input impedance, I'll do this. If I want a high output impedance, a low output impedance, I'll do this, etc. And then we'll, next lecture, we'll talk about how to properly bias a bipolar stage. Okay.